Good morning, afternoon, evening, depending on where you are. My name is Jack Dekkers, Iowa State University, and I'm one of the co-PIs on the AG2PI grants that we received from NIFA to build this community. And we're very appreciative of the funding that NIFA allocated to this. So today will be field day number 31, and it's actually our last. So our has ended, and so we are unfortunately also going to be ending the field days. But yeah, I think we have had a very good run, and we're saving the best for last. So these are we're going to hear from 2 coconut grants. So those were the larger seed grants that we awarded based on the funding we received from NIFA. And we're going to have 2 assistant professors. So we're also, one of the things we try to do is provide the funding to young scientists and their collaborative team, and allow them to develop collaborative teams. And so we're going to hear about digital tools for agriculture research. And the first presenter is Dr. Trevor Rife. He's an assistant professor in the Plant and Environmental Sciences Department at Clemson University. And he's going to talk to us about development of robust imaging systems in the Fieldbook app. And before I turn it over to Trevor, if you have questions, please put them in the chat. I'll keep an eye on the chat. And if the question is immediately relevant to what Trevor is talking about, I'll interrupt him, but otherwise we will save the questions to the end. So Trevor, please go ahead and share your screen, and the floor is yours.
Right, thank you, Jack. Let's see if I can pick the right one to share. Look good?
Yeah.
Awesome. So yeah, thank you both Nicole and Jack for organizing this, and also of course AG2PI for funding all of this work. I will admit I was a little disappointed, and people that I have talked to have been a little disappointed that I'm not actually working on coconuts. But it's been a great opportunity to bring in some development and improvements to the field book nonetheless. See, there we go. All right, so I think as many of us know very well, phenotyping is core tenet of plant breeding. And phenotyping itself is really just the act of measuring those physical characteristics that are really essential for genetics and breeding progress. So as we think about animal and plant improvements, phenotyping and collecting those phenotypes is probably the biggest bottleneck right now. We've seen these huge advancements in genomics over the last few decades, but the complementary advances in phenotyping haven't been quite as there. But so even small breeding programs often have to phenotype thousands of individuals, which means that they have to prioritize which traits they're actually phenotyping, and often have to skip traits or individuals for some perennial crops if they don't have the time or resources to collect all of the phenotypes that are of most interest. Of course, on top of all of those challenges, many of the most important phenotypes in breeding are qualitative and subject to bias or increased error from multiple raters or having large teams working on collecting that data. For a long time, collecting data in breeding programs was this combination of scribing and transcribing these individual phenotypes. And even when I started in grad school at K-State around 2013, most of the data from the wheat programs in the state of Kansas were still collecting the vast majority of their phenotypes this way. As we've seen this evolution of low-cost cameras and the complementary software to analyze the images that are coming from those, many of those programs, though, have been able to migrate toward image-based phenotyping. And really what I mean by image-based phenotyping is extracting the physical characteristics of an object through imaging and then processing that image. And taking this approach allows at least some of the subjectivity of phenotyping to be removed from the measurements. Not quite all, but some. Nonetheless, there are still quite a few constraints of image-based phenotyping. You can't walk into the field and start taking photos because of the photos themselves are generally automatically named by the device that is capturing those photos. So here, just as an example, some puppy pics that I snapped the other day at dinner. There's no information about what the content of these photos are, where these photos were taken. We have the name of the photo and a timestamp, and that's it. And so trying to utilize some of these photos for breeding or research would be extremely difficult. Now, the solution that a lot of programs have taken historically is to hold up a label in the photo and then post-process that information from the photo, which I would argue is still a pretty big constraint. If the label is handwritten, it is often impossible to parse out the information in the label, having been around enough plant breeders to see that their writing is on par with most other doctors. And even if you include a barcode, that extra step to get that actionable data from the image itself is really a barrier for progress and adoption of additional tools. Finally, there's the 5,000-pound elephant in the room of data management. And what do we do with these images as they're collected? Where are they stored? And how are they managed? And these are all issues and constraints before we're actually getting to the analysis part of extracting phenotypes from those images. So about a little more than a decade ago, we started work on this mobile application to solve some of these broader constraints of image-based phenotyping, but also of phenotyping in general. This is an app that we've developed called Fieldbook. This is a free and open source Android app that's available on GitHub and Google Play. And I think I have a quick poll just to sort of gauge the controls are over here now. Gauge the knowledge about this. And so if you wouldn't mind answering the single question, really easy question that I have thrown up there just to get an idea of where the audience is with the knowledge of Fieldbook. That's a pretty high participation rate. I don't know what the other polls are, but we're like at 91, 95%. All right, this is great. I don't often get to talk to audiences that are about 50%. Let's end this now.
So Trevor, we can see
There we go. I did it. Yeah. Good. First time doing a poll, so appreciate the patience. So it looks like there are some people that, a majority of people know of it. Plurality of people, majority of people don't use it, which is totally fine. We're gonna kind of walk through what Fieldbook is, kind of some of the design decisions that we've made, and continue forward with that. Okay. Yes, Jennifer, the community does rock. Thank you. So Fieldbook fundamentally is this way of collecting these phenotypes in plant breeding programs. Ultimately, the layout is designed to make it really easy to navigate between different individuals. So these black arrows move between different plots or entries within a breeding program. And then we have the capacity to collect different phenotypes and types of phenotypes as well. And so these small green arrows move between different traits that we have created within the app itself. And each of those traits has a customized format and layout that really optimizes how that data is entered to ultimately minimize mistakes as data is being collected. And so just to get a broader idea of what these different traits look like, we have, this is a non-exhaustive list at this point. It's grown quite a bit. But all of these traits are kind of designed to really make things efficient. And I'm not going to go over all of them today. I really want to focus on photos. And so photos have been, it's been possible to capture photos in Fieldbook since about 2015. So it's a very old screenshot that I found. And the process for doing this is, we launched the system camera app, we save the photos, and then we name and organize those so that the subsequent processing is simplified. And I've talked with many breeders that have told me that this is probably the biggest selling point of using this app. The photos that they had collected previously had many of those constraints that I had highlighted. But even with like this great implementation, in my completely unbiased opinion, there are a lot of limitations, right? So we're only able to use the system camera. And depending on the device you're using, this might not be viewed as a limitation, but for many programs, the devices that they choose to adopt and choose to distribute to their students and technicians are really inexpensive, politely bottom of the barrel devices with kind of crappy cameras. And so the type of images that we're able to capture is really limited. The quality of those images is limited by that camera quality. The original implementation of photos was developed by a graduate student who was learning how to code. And so it wasn't exactly the most optimized storage solution. And so I've taken a step back from the coding world, but that was also a limitation as we started this project. But as a consequence of that unoptimized storage, when we started collecting large image data sets, the tablets or the phones would often slow down to the point where it would be difficult or impossible to capture additional images. So I want to highlight some of the opportunities that we kind of saw when we were putting together this project. So one of the big ones is this idea of having these external fixed cameras. And so this is an imaging setup where someone has strapped a tablet to a little boom arm here with a light to provide additional lighting for the image capture. This isn't really ideal, in my opinion, because you're going to be interacting with that tablet while it's capturing the images. So touching the screen is going to bounce everything around. So we really want to fix that by having some mountable cameras that are stationary while we can control them from the tablet. We also want higher quality images. And so I think this actually is an image that was captured from one of those bottom of the barrel tablets. And as you can tell, at least on my screen, it's not the highest quality. In terms of image analysis, for many breeding purposes, this isn't explicitly necessary to have the highest quality images, but for a lot of genetics purposes where we want to collect those finer phenotypes, we really do want those higher resolution images. Finally, there are this new class of devices, which I think I will have some time to talk about at the end of the talk. And these are great. These are like e-paper devices, so they have this Kindle-like screen. The only downside is that many of them do not have cameras. So if you want to implement any kind of image capture into a breeding program, it has to be done outside of that device, or you can't use that device for that image capture. So going forward into what we set out to do, the work that we set out to do for the AG2PI project that we put in, we wanted to extend Fieldbook with external image capture and optimize that file storage. Conduct a citrus case study to test the hardware and evaluate the effectiveness of the setups that we have designed. And then finally, develop some hardware and workflow recommendations so that other groups outside of ours can adopt some of these cameras and systems and platforms to be able to collect the data that they need for their programs. Going to do things a little bit backwards and sort of give a baseline of what an imaging workflow looks like from the perspective of a Fieldbook. This is sort of the short course for Fieldbook. So I'm not going to cover everything. I'm going to skip a lot of details, but I do want to just kind of give a baseline of where things were before we started this project. And so designing a field file that would be imported into Fieldbook, it's pretty straightforward. We have this unique ID that we assign to each session that we're interested in, and then a couple pieces of other information, including the row and column or the field location points for each individual as well. And then save this as our image project 2024.csv, and then we can bring that over into Fieldbook and start our image capture workflow. And so starting up at the top, the first thing we want to do is to import that field file. So we're going to go into fields. Here's a list of the existing fields. We're going to add a new field. And after we get that imported, we now have this field listed, which the name matches our CSV file name. We can see that it was imported a couple days ago. And we have 30 entries. I truncated it for PowerPoint, but there are 30 entries in this file. Once we have that file loaded, we want to define what data types we're actually going to collect within the field. And so going back to that main screen, next thing on the list are the traits, and this is where we define those characteristics that we want to actually capture. So going into traits, we currently don't have any traits in this screen, so it's just completely empty. We can add the traits with this big plus button at the bottom, which brings up this dialog where we can type in this example trait name called tree front and save that. And once we save that, that's added to the list of the traits that we have here. So we have our field plan. We have the trait that we actually want to collect, these images of a tree front. And now is the time to actually go and collect that data. And so aptly name, we're going to go to the collect screen, which opens up that screen that I highlighted earlier. This is just, we're on our current traits, the tree front trait. We're on plot 1001. And to take a photo, we're going to use this big take photo button, which opens up our camera with this nice picture of a orange tree front. We're going to save that photo, and now we have the thumbnail for that photo displayed, and we can take additional photos of that same tree if we need to. And then finally, going to skip phenotyping the other 29 individuals, and we want this data out now. So we're going to export this data, going to the export option. This is a dialog. A lot of these options we don't need to know about right now. The most important that I want to highlight is this bundle media data with export file. And what this really does is takes all of the data that's in our field, puts it into a single zip file so that we have that all localized into one place to move between devices. After that's exported, we also have a shameless plug for citations if you do use Fieldbook in your research. And then we have our file exported. So what does that exported file look like? And this is what that bundle looks like. So here we have the zip file, contains the different data that was collected. And at the bottom of this list, we can see this image that was captured. And if we parse out those individual components, those connect back to the plot ID that we were taking the data on, the trait name that we had designed, the image rep, which in this case is wrong because I used a different sample, and the timestamp of when that image was actually captured. And so that's kind of our baseline for where we started as we worked to make improvements to the system. And so next I want to talk about some of what we actually did on the Fieldbook development side. And I will say that while a lot of the features that I'm going to be showing here are live in the active version of Fieldbook, there are a few that are still under development and either have pull requests on GitHub that will be merged in the next few weeks, or even further along than that. So biggest thing that we have worked on is file management. And the biggest component of this has been embedding image metadata into the images. And as many people here I'm sure know, metadata is the data that provides information about other data. And so this would be something like the timestamp that a data point was taken or who took the data point. And if we think back to how those images were actually named, we can see that we have a lot of the metadata that we might be interested in embedded directly into the image name. So we have the plot that it was taken on, the trait name, the timestamp. The problem that we've really found is that this is a really unreliable way of embedding image metadata. And we're also limited in what we can embed. And then on top of all of that, this image metadata completely disappears if anyone changes the file name or adds extra characters that might break any sort of operating system, naming conventions, things like that we have to strip out. And so we wanted to take a more robust approach to that metadata embedding. And the way that we did that was by using EXIF tags. And this is a component of images that all images taken from cameras have. But it's a way that manufacturers can essentially embed all of the information about the image. So the lens type that was used, the location, all of this information can be embedded right next to the actual photo itself. One of these tags that's available for people to write to is a notes tag. And so what we've done is develop this structured JSON object that we embed directly into that notes tag that contains all of the information about the photo that can be programmatically extracted for subsequent analysis. And so in this case, you can see that we know which study this photo belonged to. Here's the mouse. Which observation units, or which plot this photo was taken on, details about the actual trait that was captured, and then who collected it and when they collected it. Second, on the file management side, was really optimizing the storage. And this was fixing some decadal mistakes that I made when I did the first implementation. I don't want to get too in the weeds about the technical aspects, but the short summary is that everything is done a lot better now, and it's much faster. We've also changed quite a bit on what the actual preview looks like, and how the capturing of the images actually happens, and what options are available for users while they're capturing images. So this looks a lot like the image that I showed in that initial workflow. The one big difference is that we now have the settings option right here. So clicking that, we can see that we have a couple of choices. We have that system camera, and then we also have this custom camera option as well. We select that custom camera option. We have an option to show a preview and then to select different resolutions that camera supports. So selecting that preview shows us this expandable preview. And so we no longer have to switch between Fieldbook and a subsequent app to collect any of that data. It's very speeds up image capture immensely, not having to do those back and forth. And then the complementary part of this was improving how traits are actually created. So if we just go into this, back to our trait creation screen, and look at this dialog now, this is a really big push to, again, clean up historical inefficiencies in the code. But we have all of our different formats that we can create listed here. If we select photo, in this case, we have the different photo sources, which I'm kind of spoiling the next slide. But we have the different photo sources that we can create as different traits or data types that we want to capture. Oops. All right. Finally, we've really worked to expand the camera support within Fieldbook. And so, as I stated, when we started this work, really the only cameras that were supported were the system camera, which has those limitations of you really can't swap it out because it is part of the system. The first cameras that we started looking at implementing were USB cameras, for a couple of reasons. First off, they're relatively inexpensive compared to some of the other cameras that are available. They also have a lot of different form factors, and so they can be used. They can be kind of custom used to the application that might be needed. We really wanted some wireless option though, and we played around with a few different choices before settling on GoPro. And the GoPro cameras were really chosen for also a couple of reasons. The biggest was that they have a completely open connection protocol, so adding support for these was relatively painless compared to the next item. But they're also very accessible. And so breeding programs and breeders can easily get, if they haven't already, one of these GoPro cameras and quickly set it up and use it for image capture. Finally, we focused on adding support for Canon cameras. And this was an area that we went back and forth on quite a bit. The biggest challenge, or the biggest reasons for going with Canon cameras, was that they have a wide range of price points. And so you can, at the low end, you can acquire a camera for a few $100s, but at the high end, you can get very high resolution cameras for multiple thousands. And second, they're relatively open. They use a protocol that we kind of had to reverse engineer a little bit, not too much. And that is sort of the recurring theme with this project, is that for all of this work, there is no standard for image communication. And so the challenges that we had often were that we had to deal with different software development kits, different libraries, proprietary protocols. And we were asked a few times to sign different NDAs to actually access some of the different cameras that we were trying to implement. But we wanted to keep things as open as possible. And so those were some of the reasons that we chose this collection of cameras, which is to say, not all cameras are going to be compatible. But this is, we're willing to work with people to integrate cameras. It's really a manufacturer constraint. And so next, I want to kind of highlight why, and some use cases, or a single use case from each of these that really demonstrates their practicality for different breeding data collection. So the odd looking camera at the bottom of the USB section was a USB microscope camera, which I had never seen before until I got asked about some pollen imaging, and thought, well, this seems doable. And so we purchased this camera, popped it into a microscope that we have here at the station that I'm at, and we're basically plug and play. And it was amazing to actually see this work straight out of the box without any sort of painful setup. Of course, the images that are captured are named with all of that metadata that is really valuable for a breeding program to process the number of samples that they do each season. And so this is I got the cheapest of the least expensive of the microscope cameras that was available. So this is just a 5 megapixel microscope camera, and this is a picture of a carinata seed. It's a Ethiopian mustard, about the same size as canola seed. So it was really able to capture some high quality images, even with this relatively low resolution camera. With GoPros, the biggest advantage of those is this wide angle that they're able to capture. And so these are 2 photos that were captured, one from a kind of common cell phone and one from a GoPro at the same distance from this tree. The GoPro is able to capture a lot more pixels in the image, which is, for some applications, extremely useful. But this is really one of the big value adds of having GoPros, or GoPro support. And then finally, with the Canons, we really wanted to target things like fixed imaging with these high quality cameras. It's not currently any sort of cropping season, or we're not near the end of the season, so I don't have any fresh produce or corn ears to maize ears to take images of. So this was just an example of a really simple setup that we have been doing, or that we can do at the station that I'm at. So finally, I kind of wanted to talk about the citrus case study that we set out to perform. And I think the first question is probably, why citrus? I have this giant picture of wheat behind me. So why do we want to work on citrus? And so this was really some work that was led by Heather Manching at North Carolina State University, who kind of created this project based on her challenges with the existing fieldbook imaging options. And the challenges, so file storage, all of those were led to this project. The citrus breeding itself, like many other crops, but is even more extremely bottlenecked by phenotyping. Just to put things in perspective, the ARS citrus breeding program has 40,000 trees in its collection, has a season from August to March, which I did some quick Excel math is probably the best way to put it. And that really means that if everything was perfect, you have about 15 minutes maximum to phenotype every tree for all of the traits, which is pretty optimistic, number one, but also you want to phenotype it multiple times, and a lot of the traits that you're most interested in crops like these are things like quality, flavor, acidity, which are time consuming and really expensive to measure. So finally, white citrus, it's really amenable to image processing approaches. So looking at a picture of this tree on the right, it's really easy to tell which fruit are still on the tree, and at least visually, which ones have fallen off of the tree. And so these are the types of problems that the image analysis and really straightforward machine learning are designed to, are really ideal at solving. All right, so back to the case study. We worked with Robert Kruger, the research leader at the ARS National Clonal Germplasm Repository. He was gracious enough to give us a couple hours to explore and take some photos of the different trees in the repository, which was an incredible experience. Anyone that has the opportunity, I would highly recommend you take it, because it was amazing to see the diversity that was in that collection. The goals that we had were to use 3 different devices, 3 different camera types, take photos of the trees and evaluate the differences within those photos of differentiating the attached versus drop fruit, kind of a corollary for yield loss, and then ultimately connecting the color of the fruit while it's on the tree to a brick score as it's subsequently processed. I will say that all of these photos that we captured were processed outside of Fieldbook. We don't have the capacity to do that within the app itself, but I'll speak to that a little bit in a few slides. And so this was one of the slow days, the Plant and Animal Genome Conference. And we were able to convince an ARS unit director and a national program leader to join us, which I know it's not their first time in the field, but it sounded like it might have been the first time in a while, which was pretty incredible to get this group of people together to collect these images. Of course, this is the part where I mea culpa and say that the results for a lot of this work are still pending, performing different analyses to compare those images captured from the different cameras. That being said, we do have some preliminary work working to identify and classify where the fruit is within the image. So this is one of the images that was captured. I'm just going to crop and zoom in here. And we can see the fruit that is on the tree is labeled as fruit on tree, and the fruit that is on the ground is labeled as fruit on ground. This is work that's being done by Jordan James at UT Arlington. In another data set that he's worked on, the yield prediction for trees has been about 1.5% error. And so there's really optimistic that we can further develop these models and subsequently get them integrated directly into the data capture process. So some of the outcomes and then outlook from the work that we did. So this is a non-exhaustive list of compatible cameras. When we started this project, this was essentially a blank slide. We've added compatibility for I don't even know how many different types of USB cameras, because we do support this UVC protocol, which just stands for USB video class. This was the easy one. That's why we did it first. It actually has a protocol that we can attempt to support. It's just a matter of the cameras actually supporting it and implementing it correctly. So most USB webcams work with this, and a lot of other inexpensive USB cameras are compatible as well. On the GoPro side, the API and library that they have supports back to GoPro 9s. And then we have each of these devices, so we've been maintaining support and fixing different quirks about each of these as they've been released. On the Canon side, we have a lot of the support is semi-theoretical, but based on the approach that we eventually took to implement the support, we do confident that most of these cameras are supported. We've tested the top 3 on the left, and am happy to work with anyone in the audience or that sees this to evaluate if their specific model that's in this list is compatible, and if not, what we can do to make it that way. So finally, just kind of thinking about the outlook of this project. When we kind of think about how phenotypes were previously collected, it was this 4-step process of collecting, transcribing, analyzing, and then getting results. Through the development of tools like Fieldbook, we really took out that transcription process, which is very error-prone and laborious, often requiring months of work to convert that data into a digital format. Now that we've implemented image capture, we've kind of added this additional step into this process. That analysis is not happening on the device. Those images are being transferred to a second system and generally being analyzed there. And so moving forward, what we really want to do is bring that analysis back onto the device so that those results can be viewed in real time. And this is work that we've been starting using on-device machine learning models, which we hope will ultimately democratize machine learning. Ultimately, I think that it's critical to go from collection of the data to results as quickly as possible, because if mistakes are made and those mistakes aren't identified until the season is over, the biological sample is generally gone, and we can't actually fix those mistakes. So project website for this work is at phenoapps.org. If you go here, you can find links to all of the code, manuals with a relatively up-to-date list of compatible hardware. I haven't added a lot of the cameras yet, but as we get that code merged in, I'll work on updating this website as well. Jack, how am I doing on time?
Yeah, well, I think we're still waiting for our next speaker. Actually, has been teaching, so I don't think he has joined yet. So, but there's a number of questions in the chat, so let's address those. But first of all, thanks for. Well, do you have some finishing slides, or did you want to cover?
Oh, I had some extra slides in case I was short and needed to go long, but I will stop here and just highlight that this has been a collaborative, long-term project, and I've kind of highlighted a few people who are key to this AG2PI project specifically. So Cheney Courtney is a developer in my lab who he does the real work, which I'm very comfortable saying. And then Heather Manching, of course, at NC State, really lit the spark that drove this project forward. And Amanda Holzkamp and Keo have been extremely patient in testing and identifying all of the issues with new Fieldbook editions and things like that. And so, yeah, I can answer some questions now, or I can keep going. Either's fine with me.
Yeah, I think actually Jinya has joined us. So if you can look at the chat and maybe you can answer some of them in the chat. Otherwise, we may have some time at the end also to come back to some questions for you. But yeah, appreciate appreciate the presentation and the work. It looks like very very useful um, useful software and tool, and great work you've done with the funding from AG2PI to expand it. So appreciate that. So our next speaker is Jinya Young. He's an assistant professor in the School of Civil Engineering at Purdue University. And he is going to talk to us about an open source online platform for the management of high throughput data from unmanned aerial systems. So Jinya, floor is yours.
Thank you very much. I just came back from my class, and for some reason my camera is not working. When I tested on Monday, camera was looking perfect. So I don't think I have time to fix it. So I'm sorry about, for everyone that I have to go without my camera, but I'm having, big smile, in front of my camera. So imagine that, the photo that, you're just looking at, I'm smiling, big, and very excited to give you the presentation. Thank you, Jack and Nicole, for giving me an opportunity to give a report on the outcome of Coconut grant that we got last year. And the title of this presentation is going to be Data to Science with an acronym. We call this an D2S. And this is an open source online platform for unmanned aircraft system and high throughput phenotyping data management. And before I start my presentation, this is not just my own work. There is actually a whole crew of members working on this behind it, and especially I'd like to acknowledge the co-authors Benjamin Hancock. He's a full stack web developer that is working in my group. Also Minyoung Jung, she's also in this room as well, and she's a postdoc research associate in my group as well. So I'd like to start my presentation by some history. And the history that I'd like to talk about is that this is actually the survey that is done by Ohio State University, probably a couple of years ago. And the survey, what they did was just hide this, give me a second so that I can see the full screen. And what was the greatest invention in the past 1,000 years? And I'm going to go through the list very, very quickly. And all those inventions, you see that, oh, makes sense. This is a very, very important invention that we had for the last 1,000 years. And number 10 is an annotation. Of course, without this one, you cannot, our life, the span is going to be a lot shorter, for sure. Number 9 is, gas powered tractor. And this is very important for, transportation, airplane, of course, computer, vaccination. I think this was, very, very relevant for the COVID, era that we just, went through. Radio and televisions and telephones, automobiles, and electric light. And what is the, the number one or, the best invention that we had, over 1,000 years? They just pointed out that this is going to be a development of metal printing press, Gutenberg in 1450. This was almost 800 years ago, and this, even though this is the invention that we had the longest time ago, but this has the most impact for our current lives. And looking back, why this was the most the important invention that we had for last 1,000 years. And before the printing press, all those text information has to be handscribed, and this is a expensive process to go through, and only people who has an access to this kind of text information is going to be the rich people, where they can afford to hire somebody to create this kind of information. But after this metal printing press has been developed, now we have a very easy way of generating this kind of information. Now you can go to the bookstores or the libraries. This kind of text information is very, very accessible to anybody. And this, for this reason, this, survey that is done by Ohio State, they believe that this is the one of the most important invention we had in 1,000 years. Basically, what it's doing here is, we are making access to this information to become, the, how should I say this? Easy access to anybody, not only to the people with enough the powers or enough money. Now anybody can have easy access to this kind of text information. And one step further, what is happening more recently is that this kind of information is now digitally available. This is an example in Kindle bookstores. Now you can actually access all these books without having to carry all those books over there. Now this is accessible to your smartphone. You have a Kindle ebook readers, and accessible to the the tablet, your computers. Basically this information is so easily accessible. The other thing is that this information is in a machine readable as well, meaning that we can actually program computer to analyze this kind of information, and all those the exciting the state of the art in AI development. I'm pretty sure you guys are using ChatGPT, and how they were able to do this kind of development, because all this text information is very, very easily accessible. And this kind of revolution has happened for the text media, but that looks like same revolution is happening to the video content as well. If you look at this screen over here, in the old days, in order for you to generate video content, you need a lot of investment to happen. This is an example of TV studio. Because I'm from South Korea, I'm just showing an example of South Korea TV show over there. You need professional anchors. You need a professional cameraman. You need a professional the light engineers, audio engineers. There is a huge number of people and resources required to create a content. But this is not all. In order to actually distribute this video content with others, there is another whole crew of the people working behind the scene. This is example of broadcasting studio. They are just doing all those live video switching, the transmitting this video over the air, so that people can actually receive this kind of information. And in this kind of paradigm, only big media company can afford to do this kind of video creation. But nowadays, this is a screenshot of my office right now. And this is all set up. I'm having a little bit more advanced version as at this moment right now, but I have a light thing over here. I have a dual screen. In the middle, you see my camera. This is the one that is not working at this moment. I have my monitor so that I can see what is being broadcasted out there. I have audio mixer where I can mix up my audio, microphone. I can play videos and etc. I have a video switcher set up over here. I can switch into my camera, my screens and etc. And this is in a Stream Deck where I can automate some of those multiple steps in a single button and etc. And now comparing this against the previous setup where in order to create the high quality video content, you used to need a lot of resources to make that happen. Now we are living in a world where we can actually create a video content just by yourself, but at the quality that is somewhat similar to what those big media companies are doing. And that is one thing where you can create a content, video content, but how actually you're going to share this video content with others. And in old days, I'm probably getting old to mention this, but when we create a video, how I can share this in a video with other, my parents or my friends. Now, how I'm going to do it is that I'm going to copy this video file into DVD, and I'm going to send this in the DVD out to my friends so that they can actually play this in a video on a DVD player and etc. But this is in a Google Trend search where showing that how many people are actually searching in a DVD on Google. This is in a time ranges from 2004 all the way to 2011. As you can see, this one is going downward because that means that there is less and less people use it. but what is becoming our kind of standard over here is that now you have a way to share your video without sending any physical media to others. You can just download the YouTube video. So looking at the Google trend in 2004, YouTube was not even close to DVD, but that golden cross is happening sometime around end of November 2007, 6, or early 2007. This golden cross happened, and looking at this trend, the difference between this YouTube and DVD is so huge. And nowadays, whenever somebody creates video content, where you going to download your data media, you just go to YouTube. It's free to use. You don't need to worry about the storage limit and etc. Now we have a way to to share your video content to anybody in the world in a very, very easy way. This is almost exactly the same analogy that I made earlier. Hand scribed, going to the books, then the making in a video. I mean the digitizing the text in the media. Video is they're following the same trend as well. And if you look at the market share of YouTube, this is one of the latest statistics from the sixthsense.com website. YouTube is occupying more than 98% of market share in media players in the streaming platform. This is almost monopoly over here. And if you look at the who is the what channel has the most subscriber, this is Indian record label T-Series. He has the YouTube channel which has 260 million subscriber. And what this means is that if this one group is uploading video, this video is going to distribute it to a very, very large number of people. This is even larger number than most of the the big media company can do it. And looking back now, I believe that this kind of revolution is happening to motion sensing platform as well. And this is some of the figure that I got from online. And this is how old way of motion sensing platform is collecting data. Airborne platform and spaceborne platform, you need to have either helicopters and airplane, big airplanes, space shuttles, satellite. And this kind of platform costs you, not even on the millions, billions of dollars to, get started. And not only the platform, you need to have a sensors, and this is actually one of the the survey grade high resolution metric camera that can be mounted on an airplane. The sensor itself is going to be in the order of millions of dollars, and there's no way as an individual we can actually get into this kind of area where I like to create my own geospatial data. In this kind of paradigm, this is almost impossible. But nowadays, that drone isn't becoming available to anybody. Now you can go to either Best Buy, even Walmart. You can go those kind of grocery stores. You can buy drone that costs around. There is a cheap one out there if you like to do some the high quality mapping. Somewhere around $1,000. You can just purchase a drone. You can go out. You can create your own high quality, high resolution geospatial data product. And this is almost like this geospatial data set can be only done by the big players like federal agencies or the big tech companies can do it. Now anybody can actually collect this high quality geospatial data. And this content creation is one thing, but to me, what is missing here is that I'm getting very excited about this beautiful data set. I'm so happy that I'm addicted to watching this data set. Every corner of those location that you can get very, very excited about this. The problem here is that once you create a beautiful data set, then how can you actually share data set with others? At this moment, this is the part that I believe we don't have enough momentum built up. And that is the exact area that this seed grant and AG2PI Coconut grant is trying to address. So what we like to reach in 5 years. For example, let's say you created a video content, you go to the YouTube, you can upload the data, and let's say you create a video geospatial data set, and you just come into your mind that hey, data science platform is going to be the place I can move my data, and I can share this data set with others. So with that in mind, and the motivation of this Coconut Seed Grant was, how we can actually develop in an open source, the online platform where research scientists can, already create the data, but how they can actually share this in a beautiful data set with others. And they don't need to know, where data is, located, but you're going to have, full control, how who's going to have an access to, and how you're going to visualize it, and how you're going to, collaborate with the others. So building this in open source and online platform, there is mainly 5 the main point that we had in mind when we designed this in a platform. First one is manage, of course. This data set created by this UAP platform is kind of large. So how are we going to be able to manage this kind of big data set? And collecting data is one thing, but putting this data into a form where we can analyze is another. So how can we actually, process this data and also, visualize it? And how can we collaborate with the other research scientists on this platform, and how to publish, meaning that how we can actually share this data set with others is one of those 5 main points that we'd like to address from this online platform. So, to do this, we just divide into 2 main components here. First one is an application instance, where everything is developed as containerized in a full stack web application, and we're using React in a web application, and a fast API backend, PostgreSQL database, Nginx web server, and Solidus and Redis for job management. And this instance can be deployed by anybody who has the computing resources to do so. And once somebody deploy this in a public instances, then let's say we'd like to publish this data, and where you can actually publish this data to, and that's the place where this public center catalog is coming to play. And for this one, we use STEC technology. STEC stands for Spatial Temporal Archive Catalog. This is becoming pretty much a standard way of sharing your data with the public. And we implemented in STEC browser, and we also implemented STEC API so they can programmatic access and all this stuff as well. So this is an example in application instance over here. This is going to be end user that we're going to have in a host environment. It can be either Linux servers, Kubernetes, etc. Then we have an Nginx, reverse proxy. Then this is basically, it is going to be gateway to all those application over there. And the front end is going to be React. And the backend is going to develop as an fast API. We have a database, and the Redis is going to be job management. The solid text queue is going to be the one that actually do any types of metadata processing. And everything is containerized using a Docker technology. And everything is provided as a Docker container. So you don't need to actually do any compile or anything. You just simply pulling this in a Docker immediately from Docker in a hub. Then you should be able to deploy this in instance very easily. And public catalog, like I mentioned earlier, we're going to be using STEC technology over there. And D2 instance here is going to, once they publish, they're not publishing data, they're only publishing the metadata. And this metadata is stored in this catalog, and the people can do spatial temporal query, and they can find the data that they want, and that they should be able to consume all the actual data from each of those instances using a the cloud optimized data format technology. This is the screenshot of STEC services that we got at this moment. And this is some of the example where you can actually do spatial temporal query, especially zoom into specific area. You can specify the temporal window, and that gives you all the available the geospatial data product from this region. This is one example of automobile imagery in Indiana. This is about over 200 gigabyte in size, but thanks to this cloud optimized technology, you can actually visualize this without even downloading it. So the direction that we like to go here is that, we have produced instances being deployed, but anyone who like to deploy your own instance is going to be, the other instance can be very easily deployed. And there are other, STEC services that contains, public data, the USGS, 3D LiDAR is one example. All the NASA satellite images is available through the STEC catalog. And the European Space Agency data set is also available under the stack as well. And we're going to have our own stack catalog that it can be published from each of the instances, but that they're going to be accessible through there as well. But eventually what we'd like to go here is that we'd like to secure federal funding so that we can keep doing this kind of development. But one of the main principles that we like to address in this project here is that we like to make this UAB high-throughput phenotyping data to be fair, findable, accessible, interoperable, and reusable. And this is some of I'm going to have, the live demonstration of this, website, later. This is the login screen. And basically this is, structured in this hierarchy. You need to create a project. You can create a, flight inside the project. Inside the flight, you can upload different data product that can be multispectral, orthomosaic images, different data product. If you have a LiDAR data, you can upload the point cloud and etc. And this is some of the user interface where this is going to be home screen that you're going to see, visualization of this data product, creating projects, managing projects. This is the screen that you're going to see how to create a project, etc. Adding a flight and uploading a data product, generating additional data product once you upload the data. And the cloud optimized data format is the one that we use, meaning that once you upload this file, you don't need to download this file to your local machine to use it. This cloud optimized data format technology lets you stream this data set like you're streaming your video. On YouTube, you never download video, you just stream the video so that you can fast forward to certain location. You can actually stream from the video from the middle as well. And we can do exactly the same for all those geospatial data product for this data science platform as well. And we also use a dynamic and a map tiler called T-tiler to visualize this cloud optimized data product on the screen without downloading it. This is some of the cloud optimized point cloud data format visualization example. And we have a comparison tools, and we can actually share this data product with others very easily. And like I mentioned earlier, our whole goal is make this platform as an open platform so that not only you can actually access all this data through the browser, but any of the other computing platform that know how to consume this cloud optimized data, they can actually access this data as well. So you can access all this data in QGIS natively, and the Jupyter Notebook is also another platform we can consume this data product as well. So what I want to do is that I want to switch my screen. I like to have a live demonstration of this website. So let me just log out. So this is the the login page and the URL. And just keep having this control screen. This is in a PS2. .d2s.org. PS2 is not a PlayStation 2. It is actually a Plan Science 2.0. This development is not only funded by AG2PI, but we have some internal Purdue Purdue internal grant to to this development, which is part of Plan Science 2.0 initiative at Purdue. So this is in a Purdue instance. And you can just click sign up to create an account. And I'm not going to do it. I can create I can log in using my own credential. And this is the page that you're going to land. And going to the My Teams page, you can create your own team. So by clicking this and add a new team, you can give a name of a team, description of the team, and search by name, whom to add to these teams, and etc. This is the example of my research group, Geospatial Data Science Lab. These are all of my members. I can add more members. I can move some of them if I needed. I can create multiple teams and as well. So this is the sections where we can manage your team. And now going to the workspace, this is the place where you can manage your project. So you can create a new project, for do so, click create button here. You can zoom into the region of your interest. Let's go to Purdue Acre Farm. This is a Purdue Research Farm over here. Let's say that this is my field. Then what you can do here is that I can just click, draw this in a boundary, manually in this way. Then you have polygon, give a name, description. If you have planting date, type that information. If you harvest date, you can put type that information there. You can assign to a specific team. So any member in this team will have an access to this project that you just created. And you can also, if you already have, your field boundary file as in a shape file, zip them up and upload this shape file by clicking this, drop the zip file here, then you can actually, you don't need to draw it manually. You can actually import that in the polygon into this process as well. You can click create, then your new project will be created, which I'm not going to go to. And as you can see, we already have a lot of projects being added over here, and we can search by keywords. So, for example, there is a PPEG the field, which is the Purdue. I don't remember exactly what the P stands for, but the name of some location, but the Purdue Agriculture Center. This is the collaboration with Dr. Diane Wang's from here at Purdue. And this is a soybean trial. So you can just see that the PPEG in I1 and PPEG M2, two different projects has been created. Let me just go back, sorry. Just find the PPEG again, I1. Then you see that there's been already many projects and a flight has been added, but when you create a new project, there's nothing there. You can add a new flight, type in, when the flight was done, what is the altitude, side and forward overlap, which sensor you use, you can specify. And which platform you use. If you don't have other platform, you can choose an other and type in the name of the platform. Who is the pilot? And I assigned this to my research groups, and all the members in this project will be shown up over here. Then click create, then the new project will be created. And this is an example of, let me see that, multispectral data here. So once you create a flight, then there is going to be edit flight, which is going to be the editing information there. Manage data, then you can actually upload raw data over here and different data products. So in order to do so, click upload data, then you can choose whatever data product that you like to upload, DSM, point cloud, ortho mosaic images, raw data or others. You can just type in, for example, you have an NDVI layer being created. You can just upload it over here as well. And you see the two data product has been uploaded, auto mosaics and DSM. We can also do some, processing over here. For example, if you like to the NDVI, for example, you need to have, specify which band is in the red. In this case, it's going to be 1. Near infrared is going to be 5. And if you click, run over here, now you're going to come back, and we're going to see this in NDVI computation is happening on the server side right now. And once this processing is being done, then this data product will be available later, and we can just do that kind of stuff. And on this left side, all the flight card is available. So if you like to go to other date, for example, here, probably there is an bug here. Let me just go back. Oh, is it my internet? You guys can hear me okay, right? The website is not responding.
Yes, we can still hear you well and see.
Okay. Let me just sign out and sign back in. I hope that I haven't crashed the website. Let me do a quick check. This is the danger of you doing a live demonstration. Let's see.
We've all been there. So.
Wow. This is first time that I'm experiencing something like this. Well, let me see if I can use another browser if this helps me. Okay. Let me just log into another browser. Looks like it might be a Safari issue. Give me a second. I'm logging in another browser right now. Okay. Sorry about that. Technical difficulties.
It's
So
all right.
let me just to find. I'm always showing this in workspace here. I was working on PPAC in I1. And you can just see that was the one that was working on last time. And you see that now NDVI layer has been generated. And you can actually see this in the data product. You can go to another flight and on the left and etc. So this is the place where we can actually manage your project over there. For example, let me just go back to the PPAC again. And you can also manage access, even though you already have a members. If you would like to add additional member outside the team, you can search by those members and add them to this one as well. So this is the place where you can manage your project. But this was then the landing page once you log in. Okay, then what you need to do is that, let's say I like to find this in a PPAC data again, just click here, then all those flight is available. Click this in a data product, click orthomosaics. Then you're gonna see this in high res and orthomosaic images being rendered automatically. And let me go to the one that we just created, the multispectral. Then if I go to the one that we created, the multispectral, I believe this was the one, NDVI being created. So this is a multispectral data that we got. And this is a natural color composite. Sorry. Natural color composite, but you see this is a multispectral. Now, if you like to, the color infrared, I can choose 5, 1, and 2, click apply changes, then you're going to be able to see these changes happening on the fly. If you choose this DSM, you can choose different color map. For example, if you like to use a rainbow, this is happening. You can change the range of value to the min max and click apply change. This happens. You can specify the range of value to be, I'm only interested in 180 to 190. Apply changes, then you're going to see this being applied and automatically as well. And coming back here, we also have the point cloud visualization available as well. So you can just zoom in. This is the data set collected by LiDAR. You can see all those point cloud data sets readily accessible from here. Back, PPAC. Again, we have a comparison tool so that I can like to compare flight done in 25th and the earlier one, for example, orthomosaic here, then you can compare these two before and after in such a way, and etc. But the real beauty of this is that you can actually manage this data set here. Okay? But the more important thing is that this data set is also accessible from this outside of the platform. For example, if I just go here, let's say that I like to make this orthomosaic, I like to share with others. Right now it is restricted, meaning that only person who has an account on this platform and already have an access to this project can see it. But I can open this up, making it available to anyone. I can just copy this in a link here, send this link to the others. Then what others can do here is that they can actually consume this layer in QGIS. So it may look like I'm just showing the data set on my local machine, but let's say I open up this orthomosaic images. I can go to the source over there. And if you look at this source here, I'm not actually loading this data set from my local machine. This data set is to be pulled from this PS2 website. So all this layer they are looking at is the pulling from this data to science platform. I can just load up this QGIS DSM. Let me just zoom out. And I can just, this is in a regular file, so you can just do all different symbology here. And I like to set this to be 188 to 189. Click apply. And you're going to see that this map is being generated automatically. Now enable this map over here. Now you can just do any type of the analysis capability that is available from QGIS, and now you can use it. And we have this plot boundary plugin that we publish. For example, let's say that I'd like to delineate this in a plot boundary. I'm gonna say that I'd like to save this to my desktop. Where is it? Test 5. I'm just saying, and I like to have, for example, 10 row and 12 columns. What is an upper left coordinate? I'm gonna be just clicking this in upper left coordinate there. Plot width is gonna be 2.3 meter. Plot height is gonna be 40 centimeter, 0.45, 0.8, -2 degree in rotation, and click generate. And you may think that there's nothing there, but you see that this in a plot boundary is being generated. You can do zonal statistics from here. And the beauty of this is that now I haven't downloaded any of this data to my local machine, and this can be shared with anybody anywhere in the world. And not only we can just do this, we can also access this from, call this out, from the Jupyter notebooks. So this is the one example code in a template that I created. I just have imported the OS module and alleviate module, specified the t-taller. And this is, as you can see, I'm pulling this the specific data product from the D2S platform, getting the boundary, adding this layer, adding some color. Then the simple displays map. This is inside Jupyter Notebook. You're seeing the same location. And this data set actually are being pulled from this data science platform. Imagine that now you don't need to worry about managing your data set. All the data set is being streamed from this platform. I'm just displaying over here, but you have a certain code that you develop doing certain analysis over here. Now you don't need to worry about how you're going to manage the data. You can focus on your time and effort to the creative work, and etc. So going back to my presentation, I hope I'm doing good in terms of my time. And
if you want to wrap up in a couple of minutes,
sure. Almost done. So we actually gave a workshop in NAPPN conference in February. And as part of this conference, we developed a documentation pages. So if you go to this URL, there is the Gitbook documentation available. This QR code is going to be also available as well. And the video, we also recorded the NAPPN workshop as a video. So this the recorded video is also available in our YouTube channel. If you scan this URL, you can actually see this as well. And I'd like to thank AG2PI to give us some funding to start this development. Like I mentioned earlier, this is also supported by a Purdue internal grant, which is in Plant Science 2.0 and the Purdue Digital Forestry Institute as well. So these are some of the additional team members that I mentioned earlier. Ben and Minyoung is there, but also Dr. Cheryl and Na, which the faculty in School of Art. So a lot of UI UX the development was in collaboration with this group as well. So with this I'd like to stop my presentation, and happy to answer any question you might have.
Okay, thank you very much. Very impressive. I mean, I think it's easy for us to forget how much computation and information sharing or transfer there is with every click, and then how fast things reacted. So very impressive. There was a question in the chat. Let's see, where is it? Okay. So question from Seth Murray, and that's about the cost of storage and computing if it's centrally hosted. How is that paid for, or when others use it?
So at this moment, if Seth, if you have 120 terabyte of data, we'll receive it. We have enough storage to do it. So you can create an account. You can just start using it right away, and that's one way of doing it. But the beauty of this design or architecture is in the distributed system, and we have all the source code in open source. If you go to the Gitbook the documentation page, we have a link to the GitHub page. And if you like to actually build your own Docker images by yourself, and we also make those built images available in Docker Hub as well. So you can actually pull from this in the Docker Hub directly as well. So if you have, what I like to do is, and I like to give all those teams have their full control in terms of deploying this managing on data set. So if you like to contribute your data to our Purdue instances, we'll be more than happy to receive it. But if you like to start your own instances using your own computing infrastructure, either that to be in a Texas A&M data center, or it can be in AWS, can be Google Cloud, it really doesn't matter, what kind of company resources is out there, because, most of the public cloud services, they will have, a very well-established, procedure to deploy these, Docker images. And you can, create your own instances and just, manage your own as well.
Okay, great. That's very, very much appreciated. If you have a question, please raise your hand or just speak up. While we're waiting for additional questions, I have one, and it was kind of raised with Trevor's presentation also. And thanks to Trevor for answering all the questions in the chat. But the question was, well, can you integrate, in Trevor's case, the Fieldbook, could he integrate videos or images from UAS systems? And Trevor, you answered that, Fieldbook is really set up more for the medium throughput rather than high throughput. But question to both of you, is there a way that these systems can be linked?
Trevor, can I go first?
Yeah,
sure.
go for it. You can,
that's
you can take
exactly,
it
we are
all the
working
way.
together to write a proposal to AG2PI call this May. So we are, working together right now, proposing an AG2PI program, based on outcome of this coconut grant. Now we'd like to merge this into a single platform where not only you can manage your UV data set, all your field sampling data set can be managed in a single platform, so that we can integrate this into one.
Okay, great. Trevor, anything to add?
No, that covers everything.
Okay, good. Are there any other questions? So of course, these systems are very geared towards plant managing crop data. But I can imagine some similar things would be useful for on the animal side also. And there are mobile apps for data recording on animals that can be used within a barn. But I'm not aware of systems that are able to link images or link videos, integrate that with those data systems. Have either of you been aware of things on the animal side, or have you had inquiries about doing something similar on the animal side?
I mean, that's exactly what I'd like to address in our proposal that we are going to be working on. So we've been mainly focusing on the crop science, but how can we incorporate those in the animal side into this one? So we don't have an answer to your question yet, but that's going to be something we like to explore and to be incorporated in our next version. Sure.
Okay, great. There's another question in the chat. What are the limitations to using data to science resource website for external or international users?
There's no limitation. So if you like to create an account, please go ahead and sign up. And of course, you need to confirm your email, and I need to approve. And right now, I'm basically in the mode where I'm just approving, anybody at this moment.
Okay, great. Any last questions? Anybody? If not, then I want to thank Trevor and Jinja and the collaborators once again for excellent presentation and excellent examples of how the funds from AG2PI were very well used and allowing the community to benefit from it. So there are, as Nicole shared the slide, there is another workshop planned. I think that might be the last one. May 17, combined GWAS and TWAS using Sven. So sign up for that on the ag2pi.org website. If you're interested, they fill up quickly, so don't delay. As I mentioned, this is at the beginning. This is the last field day we're organizing, and I want to thank Nicole and Eddie for their work behind the scenes, making it very easy for me and for the speakers, I just have to show up and share. But everything behind the scenes was handled by Nicole and Eddie, and very much appreciated. And of course, the funding from USDA NIFA, very much appreciated. And Jinja mentioned, the next round of AG2PI funding, RFA, has been out for a while, and the deadline is May 30. So I think Christian Tobias is online. He's the program lead. So contact him if you have any questions. But hopefully we can have a good continuation of the work that was started through the seed grants, and we already hear from Trevor and Jinja that there are opportunities that there's thinking about combining these different systems and integrating them, which would be very, very useful. So with that, I'm gonna close things off and hope to interact with all of you at some future date in some other form. So thanks again.